So forgive me if I ramble a little bit on this exciting video that we're going to be doing for this week. We're coming into a brand new subject, and this is one that's been on hold for a while. I'm talking about automatic regeneration control. Now, we all know how to build a regen, right? No matter if it's a Hartley or if it's an Armstrong style. There are some ideal conditions. You know, the ideal conditions for a regen. For a throttle capacitor, for instance, throttle capacitor, you don't want 1,000 picofarad throttle capacitor. We've found that something between 150 and 250 picofarads for a variable makes a very smooth throttle capacitor. Starting with that, you want to select your throttle capacitor for your regen. Then you want to adjust the voltage. What's the ideal voltage that gives you the smoothest control through the sweet spot into autodyne or full regeneration? That's the second thing you're looking for. What voltage do I want to run the regen on? And finally, have I optimized the tickler turns or the tap on the Hartley regen to give me the best feedback control? So there's three things that we're juggling. We're juggling the bypassing that controls the feedback. We're juggling the actual feedback mechanism, whether a variometer or whether it's just number of turns on a tickler coil or it's a tap on a Hartley type regen. And then finally, we're looking at the actual voltage that we're operating the device at. Is that voltage the same as our audio amplifiers, for instance? Other parts of our circuit that are running at 12 volts or 250 volts, should we just put that on the detector? No, we found out that the detector likes to have 24 volts. At 24 volts, it smoothly goes into regeneration. So we end up with a detector that might need 24 or 36 volts to operate in its best condition, but the audio amplifier might need 100 volts or 200 volts to operate its best. You're really limited by your knowledge of plug-in coils, selection of the choke, what voltage are you going to run the regen at? I know that low voltage is very popular now. People are trying to see how low a voltage they can use on vacuum tubes. It's more exciting to try to run a vacuum tube on 6 volts than it is on 250 volts. I don't know why. Also, you know, how we handle the throttle capacitor. This is the all-important capacitor that controls the feedback in the regenerative receiver. So no matter if you've built 100 regens, the next one you build always turns out to have something that you haven't seen before, and it's almost like you're starting from scratch. But we do know a few basics when it comes to regens. First of all, we try to make the feedback or the tickler coil only as big as it needs to be to achieve good feedback across the entire range that we're tuning. In other words, don't overdo it on the feedback. It makes it harder to control. Also, we learned there's several ways of controlling feedback. One of them, of course, is a voltage. What kind of voltage are you putting on the drain of the FET or the collector of the transistor or the plate of the tube or the screen of a pentode tube? Controlling those voltages becomes very important. And finally, the way that we control feedback by swamping the regeneration through, you know, possibly putting some resistance across the tickler coil. These are all ways that have been experimented with. But of course, the ultra is to be able to use a throttle capacitor or a capacitor that comes off the feedback coil to ground or comes off the choke in parallel with the feedback to ground. These are both methods that are very popular. I've got some literature, actually pretty new to me. I've gotten 3 different books written by a gentleman called F.J. Cam. F.J. Cam was the editor of Practical Wireless magazine, and he was what I would call a regen nut. There are more ideas about regenerative receivers from this F.J. Cam from the UK than I've seen in any one place. He's got every method described quite nicely within the technology of his time, which was basically triode tubes and tetrode tubes. As we moved into the solid state era, of course, more and more avant-garde methods were come up with. But one of Cam's crazy ideas that I thought was very clever was to gang a rheostat in parallel with a variable capacitor. We all know that as we go down in frequency, you have to keep adding feedback. So you have to keep advancing the regeneration control as you go lower and lower in frequency. So he surmised, why don't we put a potentiometer in the same shaft coupling as the tuning capacitor? In that way, we can set the regeneration up either by varying the plate voltage of the tube or by simply swamping out the tickler coil, in effect, or some other way of degenerating the tube's gain. Now, we would have almost automatic regeneration control across the dial, because as we advance the tuning higher in frequency, we would have less feedback. As we went lower in frequency, the potentiometer would add gain or would increase the actual coupling effect of the tickler coil. You could also do this with a variometer style of tickler. So the variometer inside the other coil could be ganged to the tuning capacitor. Therefore, you would have almost automatic regeneration control. I have a subscriber, a longtime video viewer of the channel. Wayne has sent me some very advanced methods of automatic regeneration control that we'll be going over, okay? This is going to blow your mind when you see these things. But I wanted to start out with the basics. I want to go over two different styles of automatic regeneration control that I could just come up with on the bench. So here we go. Before I get into the methods of automatic feedback or regen control, I want to describe my test victim. I decided to use the basic kitchen regen. What you need to know is that this is a standard Armstrong feedback circuit. It's quite popular. It uses a JFET and some basic audio amplification. There are many variations on this circuit. The important point is that it works with a fixed throttle capacitor, and that throttle cap is controlled with a potentiometer. Now, I know that a fixed cap and potentiometer method is not as nice as a true, real variable throttle capacitor, but I wanted to start with something simple. Also, the target fixed bypass throttle, we've found that between 150 and 250 picofarads is ideal. So I chose a 220 picofarad capacitor as the fixed throttle capacitor to work against the 5K throttle resistor. So that's a very good value to start with when you're designing your tickler on your coils. Get a 220 in there. The premise that automatic volume control is actually even possible came from this Australian website that I found, cool386.com. His schematic looks a little bit crude, but this is where I started. The premise on his part was that somehow detecting and filtering audio from the regen could produce a feedback signal which could be used to adjust the voltage on the screen of the regen detector tube itself, thus changing its gain and the feedback. Hey, this works. He proved it can work. The thing I didn't like about the circuit, though, was that it's based on audio. As long as you have the audio and a long enough time constant, it should work okay. But like all audio-based feedback circuits, both adapted in simple RF-AGC systems like for single sideband receivers, or audio feedback as with microphone compressors, there's some pretty strict timing issues to make it work right. And when the audio goes away, eventually it times out, and that can mean a bunch of squealing with our regen. So I thought maybe an RF-based or an ultrasonic-based detector solution might be a better way to go. What do I want to control? I thought it would start with the regen potentiometer, which directly controls the throttle capacitor's effectiveness. I knew that I could adjust that 5K pot to give critical regen over the entire broadcast band. And the resistance variation was fairly modest, between 2K and 4.5K. I think there is a device out there that could mimic that resistor, and you could even control it with a voltage. That's right, guys, it's called the transistor. So here's the basic circuit. I left the potentiometer connected to the device's emitter in for convenience. It's kind of like having a setting control. I connected the detector preamplifier directly to the source of the JFET before the audio filtering through a low-value capacitor of 0.002 to favor the frequencies above the audio spectrum. This amplifier provides about 45 dB of gain above 5 kHz. This is followed by a negative voltage doubler detector, which uses either germanium diodes or Schottky diodes. This detector provides a negative going voltage in line with the ultrasonic or RF that we see on the source of that JFET. This drives into a transistor that's biased on for minimum resistance or full throttle. So the negative voltage coming out of the detector tends to lower the base bias and starts to turn the transistor off, meaning higher resistance, thus cutting throttle. Let's take a look at the results. So the basic concept of automatic regeneration control is assuming an AM signal that has modulation, and that modulation is going to be going into a detector circuit, and that detector circuit is going to be changing something that controls regeneration. So it's a feedback network, a classic feedback network similar to automatic gain control, except this is going to be automatic regeneration control. Now, I've disconnected the throttle capacitor. Okay, it's not even hooked up here. And I have a fixed capacitor and a 5K potentiometer. The 5K potentiometer brings in capacitance, lower resistance, more capacitance, increases the feedback, and you get more regeneration.
Here's what's happening. Our top story. Members have been confirmed killed in the Middle East as the U.S. and Israel continue this hour to attack Iran. In response, Iran is now...
Okay, so you get the idea. Now, when you go too far...
UAE and Saudi Arabia.
Can you hear that oscillation you get? Okay, so that oscillation is when we've gone beyond the sweet spot, beyond the best demodulation for AM, and we're into the autodyne or the heterodyne type situation. We're going to get this high frequency, high pitched tone. It's that high frequency tone that we're going to sense with the detector, and we're going to use that high frequency tone as kind of the stop. Don't advance the regeneration any further, back off. So that's how this is going to work. Sounds pretty simple. Any regeneration system that uses a throttle capacitor can be adapted to this system. So we need to find a device that can introduce capacitance based on a voltage. Okay, so the first thing that comes to mind is maybe a varactor or a varicap diode. Okay, that's a possibility. Another device would be a simple fixed capacitor that's being shorted to ground through a resistive element that can be changed with feedback. So what's a resistive element you know of that can be influenced with an input voltage? That's right, it's called the transistor. We're going to be using a transistor as a variable resistor. So that transistor, as we turn it on, it allows more current to flow, and it essentially is shorting the throttle capacitor more and more to ground. So that's going to be the attempt. Again, the type of regen doesn't really matter, just as long as you have a way to change the regeneration. Now, if we were to put another field effect transistor after our field effect transistor in the drain lead in cascode, that is a common gate amplifier, basically in series with the drain of the regen, we could use a direct voltage type system for feedback. Okay, that's another way of doing this. We're starving the stage basically in the drain Lower voltage, lower feedback. So that's another method we could use. So we'll try both of those methods as our regeneration control. The first method being the fixed capacitor with a resistance to ground that we vary. That's a shunt device. It could be a bipolar transistor or a FET. Or will we do the series common gate amplifier that basically you modulate the voltage on the drain, and that's how you're controlling the regeneration. Remember, our detected audio is always coming off the source, so we should be able to control that drain without upsetting the demodulated audio in the source. When we hear the whistle, back off. Back off automatically. That's the idea. Okay, so I have installed the little board. I still have the front panel potentiometer hooked up in the emitter of the control transistor. And then I have a 100K potentiometer that's the input coming off the source of the detector. This is the raw, unfiltered source of the FET, where you've got RF and you've got detected audio and all kinds of stuff there. That's what I'm sending into this thing. Over on the scope, I'm looking at approximately 0.55 volts. That is the forward voltage of the control transistor. So as soon as it detects something, this goes down and brings the transistor into the linear region, slightly turning it off. Remember, when the transistor is fully on, the capacitor, the throttle capacitor, is in circuit, totally in circuit. When we turn the transistor off, it's like backing off on this potentiometer, and that's your control. So with this automated control, I shouldn't have to fool with this. It should be able to reduce the effect of the capacitor through the negative feedback here.
The electronics retailer posted mixed quarterly results and provided
Lefty hired, lefty, and lefty hired. That's right, they are.
Mara, que pudi.
You're good, right?
Checks or a carrier attitude, built for people who stop asking for permission.
Wrongful death suit. About the way to treat. And you know, I made a joke last week in my column about, another independent.
Advisories remain in effect north and west of Boston through tonight, as we'll have some snow.
So basically,
freezing rain around as we.
this is pretty nice because I haven't touched the regen control. I've been able to go over the whole band. Now, is it as good as manual control? No, it's not. It proved principle. That's about as far as I'm going to go with this circuit.
Part of the county tomorrow. Friends, candles, dumb TikTok boycotts, and more. Keep up with all the online stories.
You can see over on the scope,
by listening to
as I tune,
on the iHeartRadio app, Apple Podcasts, or wherever you get your podcasts.
really doesn't take much to bring that transistor back down into the linear region where it starts releasing that capacitor.
The legal, the emotional weight.
We work with all insurers, offering on-site rentals.
You know, I'd always wondered when the illegals were flooding in. 356, Justin Timberlake's trying to sue to block the release of body cam video from his DWI arrest on Long Island.
With this automatic regeneration control method, where we're looking at the detector's source, okay, right here on the source of the detector, you're going to have RF there as well as demodulated audio. I'm mostly using the RF to go into the detector, and then we're integrating that, sending that into the transistor we're using as basically the regeneration potentiometer, except we're using a transistor here instead of this pot. It's going to be in pretty full oscillation. It's going to be in autodyne all the time until you get to a station that's strong enough to turn the transistor off and start to reduce the regeneration.
He encountered the Bathsheba blunder.
Okay. Yeah, so the impacted areas that you have, you've got Oman. Obviously, like, nothing's coming from Iran. Okay. Yeah, so the impacted areas that you have, you've got...
As you can see, as soon as you are on the station, it turns the regeneration back. Once you lose it, though, it goes back into oscillation.
Mountains were not found.
That's how I say it. Always says everything.
Ever maker.
Listen to what patients are saying about New Arch by Dr. Sell.
My name is Kim from Hopkins.
Use to get your question to us.
They decided to attack, so we had to join, blah, blah, blah. And as we discussed earlier,
Anyway, it's pretty interesting how it's working. And up here at this part, we're not into full oscillation, so I can adjust it so that it is in oscillation. But down here, it definitely is, though.
Don't have enough information to tell you what other smart people are saying, and they probably know more than I do.
Let's look at the circuit.
We can say some things about the reaction, historically, of things like spending to increases in the price.
So, as you can see in the circuit, it's made with a haywire circuit. I've just got some short wires down to the main board. 2 transistors, 2 diodes, a potentiometer, a few caps and resistors. There's not much to the circuit, but it does seem to control this regen. Any typical FET regen that uses a throttle capacitor can probably work with this system. Is this, the be-all, end-all? No. It does show principle, but it's not an ideal automatic regeneration control. So the next thing I want to try is the same detector system, but instead of using a throttle capacitor, I want to influence the voltage going to the FET. So what we're going to be doing is going into this area here and putting a pass transistor feeding L1. Basically, between the output of the regulator and L1, of course, I'm not going to be messing with this trimmer down here. That'll still be regulated. But right in series with L1, I'm going to put a pass device. It'll be a regular PNP transistor or NPN. I'm not sure which one I'm going to use yet. But instead of controlling this with this regen pot transistor, we're going to be controlling the voltage to the detector and see if we can control the regen that way. Be an interesting feedback point. So that first attempt was a little bit crude, and I wasn't completely satisfied. So I thought I would try again with this auto regeneration stuff. I returned the throttle pot to its normal connection to the 220 picofarad throttle capacitor, and I set the regen control to mid-range. By the way, don't attempt any of this unless your regenerative receiver is working properly to begin with. You don't want to be chasing 2 things. You might remember that capacitor was 470 picofarad to begin with in the previous circuit, so I changed it to 220 to get a little bit of softening on the control. This all depends on your tickler feedback situation being proper. I made no changes up front in the source connection or in the preamplifier circuit. By the way, you need a transistor with pretty good DC gain, like maybe 200 or 250, or else you might need another AC amplifier stage in the preamp. I know I'm going to hear comments like, why didn't you just use a dual op amp like a TL082? Why didn't you use a MOSFET pass device like a VN2222? I don't know. I guess the 2N3904s were closer to me on the bench. Now the detector diodes are flipped. Instead of negative output, we're doing positive DC output during detection. Certainly translating that voltage range into something to control a follower, like a MOSFET or transistor, would be easier with an op-amp, like I said. But it did work fine by using voltage dividers and a linear inverter transistor and a range set potentiometer. I was able to set up the range properly to basically go between 1.5 volts and the full rail of 8 volts minus the saturation voltage of the follower. So about 1.5 to 7.5 volts. And I was using the 8 volt regulated voltage on the input. The pass device is really just an emitter follower that tracks the base voltage minus, of course, about a half a volt. Okay, so I've got another method here. This is a method of automatic regeneration control. I'm taking that same signal that I'm amplifying right at the source of the FET. I'm going through a similar high-pass kind of situation into the amplifier. And this amplifier's got about probably 45 dB of gain. It's got a lot of gain. We're going into the 2 Schottky diodes, which is the detector, but this time it's a positive detector. Then I'm going into a DC amplifier that's controlling a pass device. This NPN device, well, it comes off the 8 volt regulator, and it's going to modulate the voltage that goes into the regen. So we start with 8 volts, and we can go down to 0 essentially. So between 0 and 8 volts, we now have control over the voltage going to the detector. Now we still have the capacitor to ground and the potentiometer that represents our basic throttle setting. It's less critical now, though, because we have this automatic feedback system. So let's see what we can do here using that simple circuit.
I don't think of the closing.
The meter is looking at the voltage that we are giving the detector. This particular station wants around 3.5 volts.
That the Ayatollah's killed a month ago. Was that the cream of the crop?
Now this station is so strong that it's brought the voltage on the drain of the FET down to 1.5 volts.
You know, there's it has to do with China. So we'll talk about that coming up here in just a little bit.
1.2 volts on that one.
When he went at a lunch.
And so Phil Wegman, one of the better White House correspondents, just really...
Phil, that is exactly what happened. I was completely shocked.
So it's completely under the control of that voltage that's being developed by the feedback network. Now, some of you are going to say, you're taking basically a 2 or 3 transistor regen, and you're adding all of this circuitry just to do automatic regeneration control. You're absolutely right. It's much more complex. It's a feedback network. But it shows that it can be done, and it can be done quite simply just by detecting the RF at the source of the transistor, the same output that's our audio output. Remember, we filter our audio output before sending it into the amplifier. But I'm taking that raw energy right at the source, which is mostly RF, and I'm rectifying that and using it to control a DC-coupled amplifier. And that amplifier controls that pass device, and we have regulation on the drain, and that's how we're affecting the feedback.
In this tough market, the name says it all. Real estate agents I trust.